Hello from Chem Help ASAP. Let's see a demonstration of a lab experiment that involves a Diels-Alder cycloaddition. The video description contains links to supporting documents, including the laboratory procedure and proton NMR spectra. Here is a scheme for a Diels-Alder cycloaddition. The Diels-Alder starts with a conjugated pi system, most often a diene. This diene is 1,3-butadiene. The diene reacts with a dienophile, literally something that loves the diene. The dienophile can be any pi bond, but it is normally an alkene of some sort, a CC pi bond. The reaction follows a 3-arrow mechanism. We break 3 CC pi bonds while forming a CC pi bond and 2 sigma bonds. The resulting product is a cyclohexene. Not all Diels-Alder reactions form cyclohexenes, and the identity of the product depends on the exact starting materials. Regardless, at the undergraduate level, almost all Diels-Alders form a cyclohexene in some form. Here is our reaction for the experiment featured in this video. The diene is on the left, and our diene is hidden in the 5-membered ring, which is called a furan. A furan is an aromatic ring, and that means it's pretty stable. Furans are slow to react in a Diels-Alder cycloaddition, but we have a way of making it want to react. Our dienophile is another 5-membered ring. This is maleic anhydride. The ring is distracting. Try to focus on this alkene, which is the part of the molecule that will perform the Diels-Alder. This alkene has 2 electron withdrawing groups on it, and EWGs strongly activate dienophiles. Maleic anhydride is a very reactive dienophile for most Diels-Alder reactions. Something interesting about our reaction is that the first step is not a Diels-Alder. Instead, the first step involves reaction of the amine with the anhydride of our dienophile. This is an amine acylation. The product of an amine acylation after a nucleophilic attack, loss of a leaving group, and a couple proton transfers is an amide. By making this amide, we have connected the diene and the dienophile. I said that furan is a weakly reactive diene. By physically connecting the diene and dienophile, we increase the probability of the diene and dienophile colliding in the reaction. That will increase the rate of the reaction, sluggish or not. Once the diene and dienophile are connected, the two undergo an intramolecular Diels-Alder cycloaddition. We can draw a mechanism to account for the reaction product. It's hard to see, but there is a cyclohexene ring hiding within this larger structure. That ring was formed by the Diels-Alder. I'm going to close with 3 comments. First comment, this exact reaction has been reported in the literature. It appeared in a 2012 paper with the citation at the bottom of the screen. This type of cycloaddition is called an IMDAF. That's intramolecular Diels-Alder reaction with a furan. Second comment, Diels-Alder reactions create new stereocenters and generally form the endo product. If you have learned about endo and exo products, you might notice that the product shown is the exo product. This reaction favors the exo product because the conformational restraints in how the diene and dienophile approach during the intramolecular reaction prevent the endo product from forming. Third comment, this reaction is very easy to perform. The starting materials are nonpolar and dissolve readily in nonpolar solvents. The cycloaddict is much more polar because of the acid side chain. Once the group forms, the carboxylic acid, it precipitates out of solution and the product can be easily isolated through filtration of the reaction mixture.
Let's weigh out our two reagents. So for the first reagent, I'm going to weigh out the maleic anhydride. Normally I'd pull this stuff out of a reagent bottle, but I had to raid a stash in another lab. So this is what I have. This is about 1 gram of material. I need about 245 milligrams of this. So, wow, that's 200 right there. That says 248. I think that is close enough. Okay, so there's 248 milligrams of our maleic anhydride. And of course, we'll write that down because I'll forget it. Now, for our second reagent, it is a liquid. I'm going to weigh it out in this 20 milliliter scintillation vial. And here is our reagent. It's our amine of interest. And let's take the top off. Re-tear, and I want about 468 milligrams of this material. I'm not sure that's enough, but it'll be close. We'll just add it dropwise. Everything's teared. That's about 200, 300, going to be close. Slow it down. Let's see, 468. That is 462. I'm going to go just a hair over. Okay. That is not 468. It is 475, which is just fine. I made this material. I don't think it's 100% pure. So a little extra might compensate a bit for that lack of purity. Okay, so there's that material. All the reagents are now weighed out, and now we're ready to go into the hood and set up the reaction. Oh boy, here we are in the hood. On the stir plate, we have the vial in which I measured out our amine starting material. I'm going to add a stir bar to that. So I weigh that in a 20 milliliter scintillation vial, and that's actually what I want to run the reaction in. So there's no more transferring that has to occur for that material. And I want to dissolve this material into about 5 milliliters of toluene. So toluene is a great solvent for this reaction. It's a really nonpolar solvent, and both the starting materials are really nonpolar, but the product is fairly polar. So that allows us to have the product precipitate out once it forms. Okay, I mean that's dissolved. There's not much to dissolving that oil. Okay, well, what's next is we need to add the maleic anhydride. And I have that material right here. We'll add that in and get this stirring. And whenever you do an addition of reagents, it's always a good idea to watch things a little bit. I don't see anything immediate or dramatic in terms of change in appearance. It may not show up, but some of that maleic anhydride has not dissolved yet. So, you know, we're certainly not going to be done until that dissolves. But I'll sit and watch this experiment. We'll take this off camera, but there ought to be some changes that'll happen before too long in this reaction. Well, it is 5 short minutes later, and you can see, I hope you can see, this is now thick with precipitate. Now, just because we see precipitate doesn't mean the reaction is done. So, just to be safe, I'm going to let this stir for about 30 minutes, and that will hopefully ensure that any starting materials that haven't combined to react will have a chance to fully combine, and we will work through essentially all of at least one of our starting materials, and then we will have maximized our product. But this will stir for about 30 minutes, and then we'll focus on how to isolate our product from this mixture. We've now waited about 30 minutes. I'm not sure if anything happened. It looks suspiciously like it did. I did put a cap on to minimize evaporation, which I don't think is a big deal. It's still pretty thick. Looks about the same, but at least we know that it's had time to react. Now, We'll go ahead and put it on ice and let this cool for a few minutes just to make sure everything's precipitated, minimize its solubility on ice, and then we'll be ready for our filtration. Well, everything has been cooling, and now I think we're ready to do our filtration. I'm going to turn on our vacuum, and we have good suction. I'm going to use some of this toluene over here. We're filtering a toluene solution, so we use toluene to seat the filter paper. And it's always worth peeking in the top to make sure all your holes are covered. That looks good. Now, we have our reaction mixture, and we'll just pour that in. I could have poured that a little bit faster and not left all that mess in the vial. That's all right. That's why we have lots of toluene over here to help rinse this out. I'm trying to use too much, but we're going to have to use something to get this out. There, that's better. Try a bit more. And tell you what, I'm going to have to, I don't have in reach a spatula, so I'm going to break off for a second and go get a spatula. Okay, that's better. Now, let's get a little more solvent in here. Again, this is just toluene, the same as our reaction solvent. And we can try to use that spatula to scrape down any material that's adhering to the sides. Get that loose so it comes off our glassware and can be caught in our funnel when we rinse this out. Now, there is a law of diminishing returns with this kind of thing. We're not going to get this looking pristine, and there's no reason to try to get it pristine. We just want to do the best we can. And when we feel like we've gotten enough, we are allowed to say, I'm done. Let's just give it a couple more. That looks way better now. Much less stuff in there. It's hard to stop. You feel like, oh, just a little bit more. But you end up wasting time at some point. Okay. Well, I'm going to declare that done. We've now transferred the contents into our Buchner funnel. We filtered it. We don't care about this waste, it's the toluene waste, but we do care about what we collected in our funnel, so that's why we use a suction filtration, and we will let this air dry, and then we'll find out how much product we got. Well, we are looking at the filtered compound. This was dried compound scraped off the filter paper onto a tethered watch glass. And the mass of our compound is 526 milligrams, which is actually, I think, a pretty good recovery for this reaction. So what's left, we really need to see if this is clean. Again, we can always show these white solids and say, wow, that looks beautiful, but of course we need to note it. Does it have a reasonably sharp melting point? Does it match a literature value? How does the NMR appear and the proton NMR? So we need to look at the characterization data, but this is promising result with 526 milligrams.
Let's work through our yield for this reaction. For our diene, our amine, we used 475 milligrams of the reagent. The molecular weight is 187 grams per mole. That is 2.54 millimoles of the diene. We used 248 milligrams of maleic anhydride. The molecular weight is 98 grams per mole, so that would be 2.53 millimoles of the dienophile. These react in a 1:1 ratio in the reaction. That is our stoichiometry. Our limiting reagent, therefore, is the maleic anhydride, assuming all the starter materials are pure. I made the amine, so I know it's not super pure. The number of millimoles for our limiting reagent is our theoretical yield for the reaction. We actually obtained 526 milligrams of the final product. The molecular weight is 285 grams per mole for 1.85 millimoles of product. This is our actual product, our actual yield. Actual divided by theoretical times 100 gives us a reaction yield, a percent yield of 73%. Fantastic. Of course, we need to see some characterization data before we get too excited. The melting point for the product in the upper right was 167 to 169.5, and that's degrees Celsius. That compares well with the literature value taken from the reference on the previous slide in this video. The literature value is 170.3 to 171.8. Here is the full NMR spectrum. You can see that this molecule has many different signals, more than we may be accustomed to seeing. Note that we do have some blips along the baseline. Those are impurities. While our product may look pure, it does contain visible impurities by NMR. These are not particularly bad or worrying, but this is indeed a crude product. We haven't purified it by distillation, recrystallization, or chromatography, so we shouldn't be too surprised to see some impurities. Here is the carboxylic acid all the way in the 12 to 13 ppm range. That looks good. It's a broad signal like acids always are. We're now looking at the aromatic and alkene region. The impurities look a little bit worse as we zoom in on them. Again, they aren't terrible, but they're hard to ignore. We have 5 hydrogens, 2 and 3 in the aromatic region. Those come from the phenyl ring. All 5 hydrogens around the ring. Our 2 hydrogens at about 6.6 and 6.4 are from the alkene. I normally expect alkenes to appear in the 5 to 6 ppm range. These are a bit further downfield. Sometimes strained rings like this bicyclic system cause signals to move downfield somewhat. The upfield region is much busier. Let's work from the left to the right on the spectrum. The signal at 5 ppm is the proton next to the oxygen. The signal at 4.4 is from the CH2 next to the benzene ring. You might expect this CH2 to be a singlet, but it has a strange shape. This is called an AB quartet, and is observed because of the stereochemistry in the rest of the molecule. We'll see this again for other signals. The next 2 signals are the CH2 on the other side of the nitrogen. We might expect this to be a singlet, but again, the molecule stereochemistry causes some surprises. The 2 hydrogens in this CH2 look much like 2 doublets, one at 3.9 ppm and the other at 3.5 ppm. Because of the stereochemistry of the molecule, each hydrogen for this CH2 exists in a different magnetic environment, so their chemical shifts are fairly different. That leaves the hydrogens next to the acid and the amide. One is at about 2.9 and the other is at about 2.5. The signal at 2.5 needs more commentary. We are looking for just one hydrogen, but the integration says 2.6. What's the deal? Well, remember that NMR samples are dissolved in solvents, and our solvent in this case is overlapping with one of our molecule signals. The solvent is DMSO. DMSO always contains water, and that signal shows up close to 3.5 ppm. That's the broad signal. DMSO's own residual signal, the hydrogens on DMSO, appear at about 2.5 and happen to fall right on top of one of our molecule signals. It happens. As with the downfield region, we do see a few impurities poking up from the baseline. That happens too. Overall, however, this product looks pretty nice. The melting range is very close to the literature value, and the NMR is reasonably clean with all the expected hydrogens in all the right places. I hope you enjoyed seeing this example of an intramolecular Diels-Alder cycloaddition on a furan ring. Additional supporting documents for the procedure and NMR spectra can be found through links in the description. Please subscribe, like, or leave a comment. Take care.